Morning, everyone, for our distinguished webinar series in AI and cybersecurity. With us today, Dr. Jueming Hu, Assistant Professor, Department of Mechanical Engineering at UND. The title for today's talk is AI-Assisted UAV Operations and Cyber Attacks in Aviation. Dr. Hu is an assistant professor here at UND. She received her Ph.D. and Master's in Mechanical Engineering from Arizona State University, as well as BS in Mechanical Engineering from Southeast University, China. Before joining UND, she was a postdoctoral researcher at Texas A&M University and Arizona State University. Her research interests includes AI, optimization, and formal methods and their application in cyber-physical systems. Dr. Hu, it's a great honor to have you as part of the webinar series. Thank you for taking your time this morning with us and sharing your research expertise, and the floor is yours.
Yeah, thanks so much, Prakash. Thanks for your introduction.
Yes, we can see your screen. You can proceed. Yeah.
Yeah. Hi, everyone. Welcome to today's seminar. So today I'd like to share my work about AI-assisted UAV operation and cyber attacks in aviation. So the first part is AI-assisted UAV operation. So we have heard a lot about AI. So what exactly is AI? So the term was defined in 1956 as the science and engineering of making intelligent machines. Over the decades, AI has found a range of applications, such as defeat human champions in games like playing chess, self-driving cars, and robotics. But why now? So why are we seeing an explosion of AI applications now? So it really is a convergence of three different communities that have come together. The first is a community of big data. The second is community in computing technologies. And the last but not least is a lot of research in machine learning algorithms. So AI is also revolutionizing the aviation domain, particularly through the development of unmanned aerial vehicles, also known as UAV, for diverse applications such as UAV taxis, agricultural monitoring, surveillance, and national security. So to know how we can use AI for the UAV operation, let's think about a use case. So when a farmer receives a UAV, what key factors should be considered before deploying a UAV on a farm for weed detection? So I think usually the first step is to think about what is the UAV's maximum endurance before recharging. Can the UAV handle today's wind conditions? So I call this as the vehicle level. We focus on the flight controller. So next, what about else? The next is to think about the mission level, how we can plan the trajectories of the UAV for weed detection. We have to make sure the drone can cover the entire farmland. Also, we have to find the shortest path to save energy. But it's also possible that the farmland is too large for a single UAV to scan effectively. So we may need to deploy multiple UAVs working together. Then this raises a question. So how should they coordinate their actions to achieve full coverage? So I call this is system level, how we can achieve multi-UAV cooperation to complete the flight task more efficiently. And in my work, so I rely on three techniques. First is AI algorithm, specifically it's called reinforcement learning. A second technique is formal methods, and also third is optimization. I'm using these three techniques to achieve or to enhance the safety, resilience, efficiency, and reliability of autonomous systems. Regarding safety, I have developed a reinforcement learning algorithms for collision avoidance to navigate the drone from a starting point to a destination. At the same time, it has to avoid static and moving obstacles. So how to find a conflict-free trajectory. Also, I have done the flight controller, how to develop an autonomous landing controller. Regarding resilience, I have a work about UAV GPS spoofing attack detection and mitigation. Then I integrate reinforcement learning and formal methods to solve the problems in multi-agent system. How to let the multi-agent system to solve temporally extended tasks to achieve task-oriented trajectory planning in both collaborative and non-collaborative systems. Regarding reliability, I have integrated reinforcement learning and optimization to solve maintenance scheduling and integrated production and maintenance scheduling. So due to the time limit today, so I'd like to first introduce my work about safety, autonomous landing controller. I will also cover UAV GPS spoofing attack, also cover the task-oriented trajectory planning in multi-agent system. So first, I'll introduce reinforcement learning briefly. So IR has achieved success in many fields like AlphaGo, playing chess, robotics. So reinforcement learning is used to solve sequential decision-making problems, which is usually formulated as a Markov decision process, also known as MDP. And IR learns to behave optimally through trial and error. This is quite similar to how human beings learn things. For example, when a baby learns how to grab a toy, so the baby will first explore the environment. After a few trials, the baby will start to repeat the actions that lead to grab a toy successfully. So in MDP, there are two important components, agent and environment. At each time step, the agent will observe the environment and get some observation. We call this as state. For UAV, this can be its current location, velocity, and also distance to the destination. Then based on these state or observations, the agent will make a decision on the action. For example, the UAV can choose to turn right or turn left. Then the environment will provide a feedback in the form of reward to the agent, telling the agent how good that action is or not at that state. Also, the environment will tell the agent what is the next state. In MDP, we also usually will see a gamma, so it's the importance of future reward. The objective of the IR agent is to maximize the cumulative reward. And the IR agent is really equipped with the following components. First is policy function, which is the agent's behavior function mapping from state to action. Second is value or Q function. It is estimates how good each action and or action is. The third is model, which is the representation of the environment, which will predict the next state and also the reward. Okay, so my first, I'd like to introduce my work about autonomous landing controller. So in this project, we focus on the Cessna 172 aircraft. The objective is to use throttle control to achieve a smooth terminal descent and touchdown within an acceptable horizontal tolerance while maintaining a stable glide path angle. So on the runway, the aircraft, before landing, it will see what is the perfect landing point. So like these, so they are the aiming point. Also, there are some markings to show what is the acceptable landing zone. So currently, the pilots usually land manually due to safety concerns and the need for precise real-time decisions near the ground. And traditional controllers usually struggle with changing dynamics near touchdown and sensitive to external disturbances like wind gusts and turbulence. So when the aircraft gets close to the ground, there will be ground effects, which means the airflow, the turbulence will generate more lift and make the aircraft unstable. And traditional controllers, they're usually challenged by constraints on smooth descent, touchdown accuracy, and stability. So these challenges motivate us to look at reinforcement learning. So IL is a model-free learning, which can handle complex dynamics without requiring accurate system and models. Also, it has good generalization, which means if we change the scenario to a new scenario, it probably can still have good performance. So the first step is to formulate the landing problem as a Markov decision process. So here we consider the observation of the state at each time step. It will include altitude, glide angle, velocity, distance to the ideal landing point, also angle of attack, and other information of the aircraft. And action here is the throttle command, which is a fraction of max thrust. The transition, so the simulation, we use a 2D longitudinal rigid body model. So the pitch is considered, and we use PyMonk for the simulation. So here is how we design the reward function. So the agent will receive a large reward if it lands within a small range of the desired touchdown point, or we think this as a successful landing. And also a reward for landing within a big range, but still it's an acceptable landing zone. So we call this as the normal landing. The agent will receive a large penalty if it lands outside the range. The agent will receive some small rewards if it satisfies the stability constraints. For example, when a fuselage angle attack is within 5 degrees, or it has a reasonable vertical rate, has a very smooth glide path angle, which is around 3 degrees. So in this project, currently we apply DeepQ network, also known as DQN. So in DQN, that leverages deep neural networks to approximate the Q function. So here Q star is the optimal action value function, and theta is the network parameter. We use Bellman equation to update the Q function. So it will adjust the current estimate toward the sum of the immediate reward and expected future reward, guiding convergence to the optimal policy. Also, we use experience replay and the target network for stable training. So here the IR agent learns optimal throttle control strategy directly from state observations without requiring an explicit system model. And here is the result. So here we see the black box here is the landing zone. So it can stop above it. So this work will presented in a conference in 2026, but I have other works about UAV safety, including collision avoidance. Next, I'd like to introduce my work about UAV GPS spoofing attack detection and mitigation. So Earth-based system receives signals from multiple satellites and determines its own position based on a process called trilateration. And several GPS signals are not authenticated, which means they could be vulnerable to spoofing. So what is GPS spoofing? So in GPS spoofing, an attacker tries to transmit falsified GPS signals, leading the receiver to believe they are in a different position than reality. So here is an example of successful GPS spoofing. So let's say this drone starts from the top right corner here and wants to navigate through this blue dashed line towards the target on the left side. And when the drone is on the purple square here, attacker transmits the falsified GPS signal and let the UAV believe it is located on this red triangle here. So if the UAV is on this red triangle and wants to achieve destination, it needs velocity look like this direction. But if we deploy this velocity on the purple square here, this will lead to a collision with the building. So this is an example of GPS spoofing and how it will affect the UAV trajectory and lead to potential collisions. So we have to detect this is a GPS spoofing and then try to mitigate it, how to respond to this kind of attack. So in the literature review, also other researchers tried different methods. So usually when we want to detect a GPS spoofing attack, we will compare the GPS data with other sensor data. For example, some researchers will compare it with some signal features, use external sensors such as IMU sensors or camera, and compare the data to detect anomaly in the GPS. And for detection method, based on the information to use, I categorize them to 3 groups. First is cryptographic approaches, which can successfully verify GPS signal authenticity, but they demand significant computational power, memory, and robust mechanisms for secure key distribution and management, which will impose a considerable burden on resource-constrained UAV platform. The second group is called signal level detection methods, which often rely on hardware modifications, such as the use of multiple antennas or enhanced GPS receivers to collect signal features, which may increase cost, complexity, and power requirements. Another detection method is external characteristic-based methods, which rely on multiple additional sensors. But when we use additional sensors, this can also introduce extra vulnerabilities, such as sensor interference. In these detection methods, I also found that machine learning is a popular choice. And also I focus on objective in these papers. So I found that people usually do the detection, but only a few of them consider how to respond, how to apply to the GPS spoofing and do the mitigation. After the literature review, I'm trying to ask myself these following questions. So can we achieve reliable detection with fewer sensors or reduced information? Can we design a framework that enables both detection and mitigation? Can reinforcement learning deliver a greater robustness compared to traditional machine learning approaches? Because we know machine learning, the performance quite rely on the data and the patterns in the data set. When machine learning sees unseen data set or unseen patterns in a data set, it will have poor performance. So we see whether reinforcement learning can get better robustness. Then this is what we developed. So we developed reinforcement learning-driven integrated detection and mitigation of UAV GPS spoofing attacks, or we call it RDM UAV. So here we consider UAV equipped with GPS and a camera. So it is also has a navigation strategy based on GPS data and another navigation strategy based on the camera or the vision-based navigation policy. So in this proposed framework, it achieves task-oriented detection mitigation. RDM UAV dynamically assesses the reliability of GPS data and transitions to the appropriate GPS or vision-based navigation policy, enabling task execution or the mission success. So when we formulate this optimization problem, so we say the objective is still to get the shortest trajectory, so to minimize the trajectory length. And it has 2 constraints. The first is to make sure there is no collision during the trajectory. And second is it can achieve the destination. So here you see this is a task-oriented detection and mitigation. So we want to use the navigation consequence, the results, to let the reinforcement learning to know the detection performance. It is good for the navigation for the mission success or not. But in other paper, they usually will include the detection accuracy in the objective function. So that would be different. Second, this proposed framework also achieves low reliance on fallback sensors. So our method only uses a camera to estimate the UAV's position after a spoofing is detected, which means we don't use a camera at each time step to compare it with GPS data, whether it's consistent or not. We only use it after the spoofing is detected, which is different from other methods. Also, we propose an improved DQN enhanced with a novel experience replay mechanism that prioritizes transitions involving incorrect detections. So when we sample the transitions, our common method is based to get a priority based on a temporal difference, which is delta t here. But we add another heuristic. So we have this value equals to 1 if the attack is detected incorrectly. Then it is 0 if it detected correctly. So here we consider it as an additional heuristic to identify transitions with high task-specific learning value. Then we test the effectiveness of our proposed framework across 3 different types of GPS spoofing attacks. The first type is random attacks. So here we say the spoofed location can be at any point on the map. And here on the left part, so the first figure shows the results during the early training stage. So here we see the purple triangle here is the spoofed and detected positions, but red square is spoofed but not detected positions. So at the beginning, early training stage, it will lead to a collision. And the second image figure is the middle training stage. So here it already can detect most of the spoofed positions, but this will lead to a longer trajectory, and this is not optimal. After the training converges, we can see it find the shortest path and detected all the spoofed positions and reach the destination. Here we compare our proposed method with LSTM using a time series data set. So here the horizontal axis shows the probability of attacks at each time step, and vertical axis shows the detection accuracy. So here we see the proposed IRDM UAV consistently outperforms LSTM across all attack rates in random attacks. So the second is we call it a replay attacks. So now attacker has more information about the UAV's trajectory or the mission plan. And here it will transmit the spoofed location as the UAV's position from 5 time steps ago. Okay, so here we see the spoofed location, it is along the trajectory now. And we see at the early training stage, still it will lead to collision, but in the middle training stage, it can detect these positions, but still to lead to a longer trajectory. And after the training converges, we can find the optimal trajectory. Still, we compare it with RSTM, and we see both methods, they experience a decrease in detection accuracy as attack rate increases. But our proposed LDM UAV still maintains significantly higher accuracy than the LSTM. This demonstrates its superior robustness against replay attacks. And the third type is the stealth attack. So now the attacker is most intelligent and knows more information about trajectory. So it has information of its current position and the previous position now. We see here, so for example, if the UAV is located at this center point at time step t-1, and then the spoofed location at time t, it will be in a donut-shaped range around this position at t-1. So here still we can see after training converges, we can find the shortest path and detected all the spoofed positions. Also, we compared with LSTM, and our method consistently outperformed LSTM. So from these 3 case studies, we come to this conclusion. So LDM UAV is robust against adversarial uncertainty and diverse spoofing scenarios. So this project and this work is published this summer in July. So next, I'd like to introduce my work about task-oriented trajectory planning in multi-agent system. Let's think about a motivating example. So here we have 2 agents, a blue agent and a red agent, and each agent aims to complete its own task and receive a reward of 1. And for the blue agent, or we call it eagle agent, it starts from the blue triangle and wants to get, for example, if it's a UAV, it wants to get charged at the blue circle here, and then capture the red agent. And for the adversary or the red agent also starts from the red triangle and then want to get charged at this red triangle and capture the blue agent. So here, this kind of task will give us a non-Markovian reward, as it will receive a reward of 1 after they finish the task. And we don't have an immediate reward at each time step. So for this kind of non-Markovian rewards, current location is not sufficient to determine the reward. Also, this is a multi-agent system, so we formulate it as a non-cooperative stochastic game setting. So this can be considered as a multi-agent version of the Markov decision process. But here we call it a stochastic game. So in this stochastic game, we have 2 agents. E indicates the ego agent, A indicates the adversary agent. And the state space is now the product of the ego agent state space and the adversary agent state space. And action space will include actions for both agents. And now we see the transition functions. It now depends on the actions of both agents. And we also have non-Markovian reward functions here, and still we have a discount factor to indicate the importance of the future reward. So here in stochastic game, the solution concept we are looking for is to find the Nash equilibrium. So in Nash equilibrium, each agent cannot improve its reward by unilaterally changing its own strategy. To solve this problem, now we are trying to use a mini machine called reward machine. It is a way to specify the task. So in this reward machine, we'll have a reward machine state. We use V to denote the reward machine state. It starts from initial reward machine state Vi, and it will have some propositional variables. We can think as events, and we have transition functions based on the state and events. It will have output function, and the output function can output the reward based on that transition. So for example, if we look at this ego agent, it starts from the blue triangle and want to reach the blue circle here. So it starts from the initial state, reward machine state V0. And here, if it can reach the blue circle at the same time, the red agent is not on the red circle, then we say these events is satisfied, and this will trigger a transition from reward machine state V0 to reward machine state V1. And this will give us a reward of 0. And next, from reward machine state V1, if it can capture the red agent, at the same time the red agent is not on the red circle, this will lead it go to the final reward machine state V end and give it a reward of positive 1. Okay. On the other side, if a red agent wins the game, capture the blue agent, then for this ego agent, it will receive a reward of -1. Okay. To solve this kind of complex task or temporal extended task, researchers usually add high-level features of the exploration history in the state space, but this depends on the predefined features or utilize state representation learning. And then what's the benefit of a reward machine? So this reward machine will provide a compact representation of the exploration history and expose the high-level knowledge of the task. This will help reduce exploration and improve data efficiency. So now we have introduced a stochastic game and the reward machine. Next step is how we can build connections between them two. So to connect stochastic games and reward machine, first we'll develop a labeling function. So this labeling function will label or map the state in stochastic game to high-level events, these propositional variables in the reward machine. And then the reward machine will receive this event as an input. Next is the output. So the output of the reward machine, it has to be equals to the reward specified by the reward function in the stochastic game. So then we make sure the reward machine is consistent with the task specified in stochastic game. Next is the method we developed, Q-learning with reward machine for stochastic game. So after we introduce reward machine, stochastic game, and how to connect in them, we still need a method to solve and find the optimal policy. So here in this QRM SG, we first need to formulate the problem as a product stochastic game to obtain Markovian rewards. So here we have a product stochastic game. So here now the state in the product stochastic game will include the state in the stochastic game and also the states in the reward machines and also from the both agents. So still it has the initial product state space. Also we have the transition function. It depends on the states in the stochastic game and also states in the reward machines. It has reward functions and also labeling functions. Then we define the Q function at a natural equilibrium in augmented state space. So now this Q star is the sum of immediate reward and also the discounted expected cumulative reward starting at the next augmented state, assuming that the agent followed the best response strategies. And this Q learning is still the iterative learning process. So at each time step, a stage game based on the current Q function is formulated. And then the natural equilibrium for the stage game is calculated use Lemke-Hausen method. The Q function then is updated based on the expectation that the agent would take best response actions. So in case study, we'll have a more complex task now. So for the blue agent, it has to first get charged on a blue circle and then also destroy the red circle and then get recharged its own blue circle and then capture the red agent. And here is the corresponding reward machine, how we can satisfy this kind of task. Okay. And then we compare it with other state-of-the-art multi-agent reinforcement learning algorithms. And we see our method, which is the result, which is the black dashed line here. So it can get converged and the blue agent wins the game. So it receive a reward of 1, but the red agent received a reward of 0. And also our method learns more efficiently than other methods. So in conclusion, we investigate the utilization of reward machines in non-cooperative stochastic games to address the challenge of data-intensive learning. And we develop QRM-SG algorithm to learn the best response strategy of each agent to constitute a natural equilibrium. The case studies shows the effectiveness of QRM-SG. And this method is also readily applied to domains such as manufacturing, autonomous systems, and cybersecurity, where competition is inherent due to limited resources. So I have one published work about this project, and also another work use reward machine, but also in a graph-based multi-agent reinforcement learning setup, and also for collaborative tasks. So in conclusion, I have introduced my 3 projects. So first, I start from the vehicle level. I have developed a reinforcement learning-based autonomous landing controller. And the next step, we are currently exploring how to enhance landing smoothness and flight stability through Lagrangian multiplier. The next, we come to the mission level about the trajectory planning. So we have developed a robust LLDM UAV framework for GPS spoofing detection and mitigation. Next step is to extend it to a 3D operational environment and enhance adaptability to unseen scenarios. For the system level, now we look at a multi-agent system, and we develop an efficient multi-agent system to solve temporary extended tasks. The next step is to design resilient UAV communication systems. The second part of my today's talk, I'd like to briefly introduce cyberattacks in aviation. So cyberattacks, here are some information about cyberattacks documented in aviation industry from 2000 to 2024. So here we can see cyberattacks that happens in airports and airlines, and 65% cyberattacks. So most of them they're on the airports, and we have 35% happens on the airlines. So to better understand these cyberattacks, let's still think about these 3 levels for the UAV operation for the aircraft. So in the vehicle level, when we focus on the flight controller, it's because flight controller is depending on the current information. We want to make decision on a control command. So then the current information, it really depends on the data collected from sensors. Then the attackers, they can focus on the sensor attacks. First, I have introduced spoofing attack, which is about to transmit falsified data. And also another type of sensor attack is sensor saturation. For example, attacker can use lights to blind cameras, or they can use radar jamming to achieve sensor degradation. Then we cannot receive accurate sensor data. This will affect our accuracy or the performance of the controller. Next is on the controller, whether it can have attacks. Yeah, so the answer is yes. So attacker is developing some hacking. So then the attacker is trying to gain unauthorized access to the systems. Then it can modify the flight control software and also inject malicious control commands. Next is the mission level. When we do the trajectory planning, how the attackers can send the cyber attacks. So first, for the navigation, one common type is data breach. So the attacker is trying to steal the mission plan or the flight routes. Another is ransomware. So they are trying to encrypt mission files or lock the operators. And for the trajectory planning, usually we'll have a ground station, which will send the mission to the aircraft. So then we have the communication now. So in communication, it's very common to have denial of service attack. So now the attacker trying to overwhelm the communication channels, then the aircraft is not able to receive the commands from the ground station. On the system level, when focused on multi-UAV coordination, still we'll have the communication between the UAVs. So still we'll have the denial of service attack. And now it's also possible to have jamming or signal interference. So the attacker will try to transmit strong radio signals. Then the aircraft then is hard to detect hard to receive the signal, or difficult to detect which signal is from its friend UAV, or which signal can include the useful information. Another is cyber attack. So now it will try to gain the trust and influence the coordination between the UAVs. So it will pretend to be a good, friendly UAV, but actually it's doing influencing not useful information or trying to spoof the UAV. So that's all about my today's talk, and I'd like to take any questions.
Thank you, Dr. Hu, for your presentation. I appreciate it. So folks can put their questions on the chat, and maybe I can start with the first question. Can you go back to your slide number 24, 25, where you talked about LSTM and the other model? And I was just curious to see, when you see the dip at 35% and 50%, why, what type of, what is the sequence length you use? What is the number of layers you use at LSTM? And what is the inference latency? Did you even explore different sequence length and compare the performance of your model? And that's one part. Second thing is, what is your perspective on bi-LSTM or stacked LSTM, versus your approach?
Yeah, so here for LSTM, I think we are using about 2 layers, and we have a window size around 15 time steps. So we are using the 15 time steps of the GPS data set, and want to predict whether the GPS data on the 16th that time step it is spoof data or not. And here the percentage here is showing the probability of attack at each time step. This is how we generate how we simulate the attacks. So here I think for the reason for 35% has poor performance, probably doesn't get enough attack data to get good performance. And when I compare these two, so I can see LTM UAV is better to handle different various attack rates or probabilities here, because they have let's see here the highest accuracy is 99%, but even when the attack rate goes to 95%, it still has a good performance as at 97%. So I think the difference here is because they are using a little bit different input or the features to detect the data. And also another difference is reinforcement learning has better generalization. So when it has a different scenario, it has better results. And for the inference of the latency, so we tested on I remember we tested on a MacBook, and I think to do a neural network inference, it will take around maybe 1 or 2 milliseconds, so it will not cause latency in a real deployment on the UAV.
Thank you.
Yeah.
Others can ask questions.
Yeah, thanks for the question, Prakash.
Yeah, thank you. Jilung or other people, other faculty or other students, this is your time to ask questions. I want more questions, please. While we wait, maybe I should ask, huh? Let's see. In terms of the reinforcement learning, you are doing a lot of offline training, or you have a combination of offline, online training in your multi-robot, multi-UAV communication? First question. Number two is when these are deployed in swarm environment in agricultural application, or do you have an architecture of master slave, or do you want these assuming that they have some GPU nodes running and they should be able to do these high compute intensive whatever that it's sensing, right? And so I'm just thinking, going forward, what is your perspective on actually when we do this multi-vehicle communication, do you see a role of cloud versus a dedicated edge devices running these algorithms? What's the perspective?
Yeah, so they are very good questions. So first, I think you are asking my training that offline. Yeah, so I do simulation or I collect the data and I do the offline training. So maybe the next step is whether we can have a algorithm running on the UAV, and then based on its sensors, we collect how the environment changes or evolving, then whether we can adapt to the new environment quickly. So that will be the online learning. So online collect a few data and we find that it is different from the data set we use in the training, then whether it can adapt to the new environment. And then the next is when I deploy this to a swarm. So another thing is, so during the training, this will have needs a lot of computations, but after training, we will only use the converged or the trained policy deployed on the UAV. So it will only go through a neural network inference. So no more training on the UAV. So that computation is not too bad for the UAV. And then for the swarm, we'll consider each UAV will be equipped with this kind of, will have a GPU like NVIDIA Jetson on board, so it will be able to run it. But still, as it gets more complex, maybe have more algorithms running on one UAV, and one has to do communication. So we are thinking about we may have a ground station or we have a digital twin framework. So in a digital twin, it can predict something and collect the data from UAV, then do some additional process on the digital twin, that ground station, and then it can send a command to each UAV. So we think this will reduce the computation on each UAV, but still can finish all the tasks, computation tasks.
Super.
Yes.
Thank you. I appreciate your comment. Questions, guys? We have 18, 20 people here. Can I ask some more questions?
Yeah, sure.
Let's see. Do we see any questions on the chat?
Yeah, I actually wanted to ask about other than the three type of attacks that you considered in the GPS spoofing scenario, other than those three type of attacks, do you have other attacks that you will be focusing on?
Yeah, this is a good question. So here you see I have a donut shape here,
Mm-hmm.
but this doesn't this is only the blue region and doesn't cover these. There's some still region we are missing, right? So this region, the white here, it is to indicate the GPS error. So I think for now it will be a challenge or an open problem how we can detect the swing attack versus the GPS error itself. So it's hard to distinguish it is come from the attack or from the GPS error or the noise. So that would be a more difficult attack to do, and we are thinking about to do these things.
Okay, thank you for sharing.
Yeah, thank you.
I have. Oh, can you hear me?
Yeah, I can hear you.
Oh, one other question. Because we talk about cyber attacks in the context of UAV, there's a lot of off-the-shelf components like IMU, different sensors within UAV, or maybe this supply chain issue that we talk about in literature in UAVs. Do you happen to look into test different types of UAV from other brands, non-US brands, and see where the vulnerabilities lie, or which of those off-the-shelf components are so vulnerable? Maybe the attack vectors is those are the high likelihood of attack vectors. So we should what are those from a component perspective, right? I think which is more vulnerable, so that the all these replay attack or DOS attack that you're talking about
Yeah.
somewhat more
Mhm.
meaningfully represented.
Yeah, I think this is a very deep question, and this is actually, I think, some research focus of the probably the DARPA Research Agency. So they are talking about the UAV is have the architecture and they have a lot of components inside. For example, from they have the data flow from one sensor to another sensor and go to the controller, go to another software, and they have these architecture, and they want to make sure these data flow or the logic flow is resilient for this architecture. And now they are talking about use formal methods to specify the logics and to make sure this is trustworthy system. So that this is very good research direction to go. But currently, I'm only using Blue, so it's the US manufactured UAV, and I haven't go through all the components in the architecture. And now I only focus on the from the flight controller and fire controller and high level the trajectory planning, and later we'll do communication. But still a lot of components we haven't explored yet. So I think for UAV it has a lot of components and a lot of things can be done here for the UAV.
Great. Any other questions, guys? Anything else? Anybody else wants to jump in and ask questions? If not, thank you, Dr. Hu, for your time. I think this is fascinating. I think there's a lot of opportunities for extending your work in different directions. So I appreciate for taking the time this morning with us to share your expertise. And you will receive a nice plaque from us. And thank you for your time. And we look forward to working with you.
Yeah, thank you so much. And thanks for inviting us. And thanks for so many good questions. Thank you.
Thank you.